I messed up and I only posted it, ended up posting it later on Facebook. But anytime Jerry presents, he's always got homework, and I only posted
Yeah,
it on the Facebook group. But
if anybody bothered to do it, we'll,
exactly.
we'll go over it at the end there. Hopefully this won't take a whole long amount of time. I just did this at the WSLS Institute, and it
Yep.
fit nicely in an hour and a half time slot with a bunch of questions and stuff. So
Perfect.
um, hopefully it'll go smoothly tonight. Uh, for those of you who don't know me, I've been in education for a number of years, and I keep trying to retire, but it's not sticking. And they're keeping me pretty busy doing things like this and other sessions and that type of thing. But Trent asked me a couple of weeks ago, I guess he had a question from somebody about talking about doing grid and ground conversions in different coordinate systems and that type of thing. And he said that it'd be a good topic to have on Mentoring Mondays. And since I had it put together for the WSLS Institute, I said I'd go ahead and do it for him. So that's what we're going to do tonight. We're going to uh, go through a bunch of stuff here relatively quickly, and then look at some computations and some things that are going to change with the new datum adoptions when those finally go through. And some other kind of like off the side type of things that you may not have considered, but are in the BLM 2009 manual that we might need to take into consideration when we're dealing with grid systems. First of all, we need to talk a little bit about Earth models, and you've probably seen this before a lot of different places. So I'm just going to talk real quickly here about the difference between, this is the very first thing I talk about when I teach a basic surveying class, is the difference between plane surveying and geodetic surveying. In plane surveying, we just assume the Earth's a flat little piece of it, our little piece we're working on is flat. And all of our calculations are simple. But once you start going longer distances, then you have to take into account the size and shape of the Earth. So, vertical lines aren't parallel, and we have curved surfaces, and strange things happen with the Earth's dynamics and all that kind of stuff. So we have to start to model the Earth. And the problem is we measure on a physical Earth, but the physical Earth isn't a mathematical surface. And we want to express things in a mathematical fashion for positions. So we have to figure out how can we fit a mathematical surface to the Earth. So we have to step through a couple of other things. Now, even though we're working on the physical Earth itself, when you center a bubble, or if anybody still suspends plumb bobs and that type of thing, you're not referencing yourself to the physical Earth. You're referencing yourself to the geoid, which is another surface. It's an equal potential surface. And it's defined by gravity pulling in and centrifugal force pushing out, which is why sometimes you'll hear the Earth referred to as an oblate spheroid. What that means, it's flattened at the poles and expanded at the equator. That's because of the effect of centrifugal force. The radius is larger at the equator, so you have larger centrifugal force there than you do when you're standing on the pole. Now, it's not real nice and neat just like that and come up with a mathematical surface because gravity is a function of mass, and the Earth is full of mass anomalies. And there are solids and there's molten parts to it, so it's constantly shifting. So it's a non-homogeneous mass. So the lines of gravity are neither parallel nor are they straight. And even on the surface of the Earth, you can see the effect when you're at the foothills by the Rockies and stuff. A vertical line is actually deflected towards the Rockies because of that mass anomaly. But the result is that this is a surface we reference to, but it's a lumpy and it's a changing non-mathematical surface. So what do? Well, we try to fit a mathematical surface to that. So again, we're measuring on a physical Earth, and the geoid is what we reference ourselves to, and that roughly approximates what we refer to as a mean sea level surface, although it's not strictly that in its truest sense. And so then what we do is we fit a mathematical surface to that ellipsoid or to the geoid, and that's an ellipsoid. We try to fit it as best as we can, but it doesn't fit perfectly everywhere because again, the geoid's not mathematical, but the ellipsoid is. So in some places it's going to be below it, some places it's going to be above it, some places it's going to fit relatively well. Now, there are two parameters that we normally work with when we're talking about how well does the ellipsoid fit to the geoid and how well does that fit to the physical Earth. And there's skewness and there's vertical separation. Vertical separation is the one that most people are familiar with. We talk about an orthometric height, which is the elevation of a ground point above our vertical datum. That's the one that you get by running levels and that type of thing. The other is an ellipsoidal height, which is the distance from the ellipsoid along a normal to that ellipsoid surface to the ground point. When GPS was first came in 30 years ago or so, and people started measuring with it and they checked benchmarks, they said, my God, the benchmark elevations are terrible. We're off like 100 feet on our benchmark. Well, it's because you were comparing apples and oranges. The benchmark elevation was an orthometric elevation, which was with respect to the geoid, but the GPS elevation was with respect to the ellipsoid. And what they were actually seeing is what's the geoid height at that location. So you got three heights. You have the geoid height. Where's the geoid with respect to the ellipsoid? You have the orthometric height. Where's the ground with respect to the geoid? And then you also have where's the ground with respect to the ellipsoid, which is the ellipsoidal height. And, and it's real simple. If we can just add those three together, the orthometric height plus the geoid is equal to the ellipsoidal height. That's not strictly 100% true, but it's close enough for 99% of the stuff that we do. Geodesists will stamp their feet and say, no, 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 that's not exactly right, but that's okay. Let them. We don't let them out very often into the real world. And when we do, we just kind of play along with whatever they say. The other thing is the skewness. And you can think of skewness as the parallelity of the geoid and the ellipsoid. How close are they being parallel? Where they're not parallel is when the vertical line, remember the vertical line is perpendicular to the geoid, that's our plumb line, and the normal on the ellipsoid is perpendicular to the ellipsoid at that point. If those two coincide, that means that the two surfaces are parallel. If there's any skewness between them, then you've got what we call a deflection of the vertical. It's the angle between the directions of gravity and the ellipsoidal normal. Now, depending on how well it fits, we can have those heights be very small, or we could have the heights be large. We could have large skewness or small skewness or whatever. For example, and when we used the Clark 1866 ellipsoid for NAD 27, that was a regionally fit datum. It was fit to Meads Ranch in Kansas. That's a control point in Kansas. And at that point, it was said that the ellipsoid and the geoid coincided. So there was no geoid height, there was no separation, and there was no deflection of the vertical at that point. And as long as we kept it at that small enough area, that was pretty much true. But eventually, NAD 27 extended all the way up into Canada, into Alaska, and down into Mexico. And the further we got away from that central point, the more error was introduced. And that's part of the reason that we had to go to NAD 83 is because it was just too much error that was introduced into it. So now we talk about spatial systems, a way we express positions or express spatial locations. The traditional way is by using geodetic coordinates. Now, we got to be careful with geodetic coordinates. You have geodetic coordinates, you got geographic coordinates. Geographic coordinates generally based on the Earth being modeled by a sphere. With geodetic coordinates, it's based on the ellipsoid. So that when we have the normal to the surface, okay, perpendicular to the ellipsoid, it doesn't intersect at the center of that ellipsoid like it would on a sphere. So the actual latitude and stuff is measured to that normal line. It's not measured to the central line. So when we look at position, horizontal, the latitude and longitude, it's the angle in the equator to the meridian that contains the geographic north and south poles in the observer's position, and the latitude, which is the angle above or below the equatorial axis in that meridian. Now that gives you a unique position, and then if you put in a height, that'll give you the elevation, or you put in an elevation, that gives you a three-dimensional position. But it's a real cumbersome system to work with from a mapping viewpoint. Okay, we don't normally work at latitude and longitude. Plus, when you work with latitudes and longitudes, you're working with angular values. And none of our equipment measures distances as angular arcs and that type of thing. And on the ellipsoid, it gets real complicated real fast because when you look at a meridian, that's an ellipsoidal section. Okay? That's got a semi-minor and a semi-major axis. That's an elliptical section. But if you look at a line of latitude, that's a circular section. When you look at something that's in an azimuth, that's another type of elliptical section. Now, the shortest distance between 2 points on a plane is a straight line, right? The shortest distance between 2 points on a sphere is what? Audience participation. You got to jump in and answer. It's easier when I'm doing this live face to face because then I can run up to people and poke them and make sure that they answer me. But on a sphere, it's an arc, right? It's just a circular arc. Do you know what it is on an ellipsoid?
Parabola?
No, part of it depends on which direction you're headed. If you're going straight north and south, then it's part of an elliptical section. Okay? If you're going east and west, it's part of a circular segment. But if you're going at any angle, it's what's called a geodesic, and it's actually an S-shaped curve. That's the shortest distance between any 2 points on an ellipsoid. So you can see that on an ellipsoid, the geometry gets really complicated relatively quickly. So to work in a geodetic coordinate system is not real handy. Plus, to express positions to the nearest, say, hundredth of a foot, you'd have to carry 5 decimal places on all of your angles in seconds. And people aren't used to doing that, so it's not a real convenient system to work with. So the other one we have that's a global one that uses a 3-dimensional ellipsoid or a 3-dimensional Earth expression is the terrestrial coordinate system, where you sometimes see it referred to as the Earth Center Earth Fixed system. And this is basically the system that GPS reports its position in, the GPS satellites. If you look at GPS satellite almanac information, it gives you this horrendously large linear coordinates. Well, that's based on the terrestrial coordinate system. And that's one of the problems with the terrestrial coordinate system is the coordinates are horrendously large because they're based on the origin being at the center of the Earth. Plus, another disadvantage of the terrestrial coordinate system is we're used to, when we map something that's a tall vertical object, like say a telecommunications tower, say a 500-foot telecommunications tower, when we map that, we know at the top is above the bottom. That's a vertical line. But in a terrestrial coordinate system, those are 2 different 3-dimensional coordinates, so they don't map on top of each other. So working with that in, say, in a mapping type of application is really cumbersome to use. So we normally don't work with these. It's too cumbersome to work with this. So we want to develop something that covers the region that we're interested in and keeps things as simple as possible. So that's when we go to a 2-dimensional planar type of system. We want to have a basic coordinate system where the rules are easier. All the norths are parallel. And the east axis is perpendicular to the north axis, and there's straight lines. And a unit of length that's consistent no matter which direction we have it. So if I've got my hands, apart, what I say is a foot, whether I orient that north-south or east-west or at some angle, the distance between my hand wouldn't change. That would be the same length regardless. That would be the perfect system for us. And it would keep the computations relatively simple because now we're working with plane trigonometry. The disadvantage to that is that's not the way the world operates. Okay, we have to, in essence, make the world fit that model as opposed to that model fitting the world very well. And there's some problems associated with that, and those are what we call distortions. Okay? We don't get a clear depiction of what the real Earth is when we put it into that system. Okay? Now, this is where doing this in person is a much more impactful graphic. The reason when I was a kid, they forced me to eat tomatoes. only food that they forced me to eat when I was a kid was tomatoes. They didn't force me to eat liver, which I still to this day don't eat, or any other, but it was tomatoes, and I absolutely hated them. So I use the tomato as my three-dimensional Earth. Okay? And I would use my surveying textbook, okay, as my two-dimensional plane. And I would project that tomato into that two-dimensional plane by smashing my book down on top of it. And basically what happens then is I wind up with people say a smashed tomato. It's not a smashed tomato, it's a distorted tomato. Right? Basically, in order to make that tomato fit into that two-dimensional plane, I had to distort it. Now, some parts of it are distorted more than other parts. The parts that are going to be least distorted are going to be which ones?
The ones near the middle?
Yeah, the ones near the middle, the points of contact, right? And where I go vertically down. The ones that's going to be distorted most are going to be the ones that are further out from that. So the further away I am from my point of projection, the more my distortions are and the weirder they behave. Everybody's seen an orange peel map of the Earth, right? Where somebody takes like an orange and peels it and tries to keep the orange peel in one piece, but you have to tear it, and when you lay it out flat, it does all sorts of weird things. That's a three-dimensional surface projected into two-dimensional plane. And the only way you can do that is by tearing the surface and distorting it in places. So orange peel maps are a good example of a highly distorted projection. Now I can take, let's say I'm looking at a piece of the Earth here, and I've got my meridians on here. These are my geodetic meridians, two north-south lines, and my east-west lines, which are perpendicular to them, so they're curved. My latitudinal lines are curved. When I look at that up close here, I see my true north-south, my geodetic north-south lines are all converging, and my east-west lines are all curved. But I want to have parallel north-south lines and east-west lines that are perpendicular to that. So I want to take that piece of the Earth and I want to project it into this plane where I've got my nice grid system here. Now I can see that very at the center of my projection is where the least amount of distortion is. As I go to a larger area, I have more distortion. You can see that my angles change in here, and we'll talk about distances here in a little bit. But the further out I go, the greater it is. If I go to a smaller area, I still have distortions, but they're not as large. So instead of trying to map the entire world, we pick a small part of it and develop a coordinate system for our part of it, and then map everything with respect to that. So the smaller, now, the other thing about these distortions is, remember when I connected the Earth to the ellipsoid through heights and skewness, and then I'm going to fit a grid system to that ellipsoid, I can connect all that stuff mathematically. So that I do have these distortions, but I can also compensate for them mathematically. They're systematic distortions. So when we're talking about ground to grid and grid to ground, that's what we're doing, is we're compensating for the distortions between those two systems. So direction distortion, 3D meridians convert to 2D do not. Okay, there's no distortion at the center, and the angle between grid north and true north is what we refer to as the convergence. So the convergence, you can see, is a function of longitude, east-west, not north-south. North-south is pretty much consistent. So longitude, so the convergence is a function of longitude. The other distortion that we have is distance, because when I projected that tomato into the plane, there were parts of the tomato that stretched until it eventually tore. But the parts that stretched actually made the distances on the surface of that tomato become further apart. So that's part of the distortion I introduced it. So in some cases, I'm taking my real Earth that's curved and it's got all these bumps and all these elevation differences on it, and I'm projecting along my vertical lines eventually down to a two-dimensional plane. Now, if my surface is above my plane, they're going to project with converging vertical lines to that plane, and my distances are going to get shorter. If my projection is above my Earth's surface, then I'm going to be projecting along those converging lines up, and it's going to make those distances further apart. That's what we refer to as scaling. So here's our distance distortion and our angle distortion. This we saw was a function of longitude, so it's systematic. This is a function of elevation and location, so that's also systematic, so we can compensate for them, okay? So now what we're going to do is we're going to use that information and we're going to create a grid, build a basic grid. And there are a couple of different projection surfaces that we can use, but the most popular ones that fit well for different types of areas are a conic projection and a cylindrical projection. In particular, a cylindrical projection that lays on its side. It's called a transverse cylindrical projection. Actually, the conic one is the Lambert conic projection developed by Geraldus Lambert back many, many years ago in Germany. And the transverse Mercator project, which is developed by Mercator, an upright cylinder, and then Lambert turned it on its side, so we actually developed the transverse Mercator also. So Lambert's responsible for both of these types of projections. But basically what happens is we take the projection, whether it's a cylindrical one or a conic one, and we make it a secant projection. By that, what we mean, it cuts through the ellipsoid. So part of the ellipsoid is above it, part of the ellipsoid is inside of it. And then when we take and we cut that open and roll it out flat, we're rolling it out flat without distorting it into a two-dimensional plane. So we project points from the ellipsoid to that surface. In some cases, we're projecting down. In some cases, we're projecting up. So that affects the scale. And then we have to look at the relationship between the geodetic meridian on here and the grid meridian that we're going to build on the coordinate system. So on a conic projection, real quick, scale varies east and west. Our scale is constant east and west. It varies north and south. So for long areas, long east-west areas, we use a conic projection because the scale doesn't vary as much. The convergence is a function of longitude. We have a central meridian. That's a center. That's where my tomato touched the book. So we have no distortion there. That geodetic north and grid north coincide there. And then that defines grid north for the system. And then as I move east and west, that my convergence increases numerically. This was a function of longitude. On a cylindric projection, scale variation is just the opposite. It's constant north and south and varies east and west. So areas that are along north and south, we generally use a transverse Mercator. The meridians are a little bit more complex on Mercator projection, transverse Mercator projection. But for the size of the area that we work, we could generally work with small sections here and say convergence still is between two straight lines, the geodetic north and the grid north at any given point. But it's a function of longitude. So basically, if we know where we are in a projection, we know something about the projection mathematics, we can figure out what all these different things are and compensate for it. So let's look at some of the systems, the formal systems that we have. Probably the most familiar to everyone's a stapling coordinate system. The NGS developed them initially for, can't remember North or South Carolina back in 1934, and then built coordinate systems for all the states. And most states run multiple systems divided up into zones because the distortion criteria was that it'd be maximum of 1 in 10,000 between the ellipsoid and the grid system. Basically, what that said is, if you had an accuracy of 1 in 10,000 or less, you could ignore the difference between ground and between the two systems. But if you needed something more accurate than that, then 1 in 10,000 was the cutoff point. And in order to maintain that accuracy, you couldn't put the whole state, say, onto one zone. You'd have to break it up into pieces. For instance, Wisconsin's broken up into 3 conic projections, and some of the other states, like California, have quite a few more because of their size. You got Florida, which has got a transverse Mercator for the peninsula area, and then conic ones for the panhandle area because of different configurations and that type of thing. So there's different combinations of these throughout. And this is a map that showed what the change was from the 27 zones, NAD 27 to NAD 83. Some states did, in fact, combine multiple zones into a singular zone. Others added some additional zones and that type of thing. But that's what people are most familiar with. It wasn't real popular before the datum changed simply because the coordinates were so large. When you were working with a local survey, say in Wisconsin down here, and you were working with coordinates, they'd be in the millions of feet, which is real cumbersome to work with, when you're doing hand calculations back before the datum got changed and stuff. The other one that most people are familiar with, and this has been a darling of the GIS community for a long time, is the Universal Transverse Mercator System. That's a global system developed by the Defense Mapping Agency. And it's got 6-degree wide zones, and they extend from, they don't go all the way up to the poles, they fall a couple degrees short of the poles simply because of how much convergence is up there. But they give maximum global coverage. They're 6 degrees wide, so there's 60 of them going around the Earth. And their maximum distortion is 1 in 2,500. So they're only about a quarter of what they are for the state plane zones. That's why their zone coverages can be larger. Now, both of these state plane and UTM were developed on NAD 27, and then when NAD 83 came in, they updated both of them for that new data, and we kind of maintain them for that. Those are the primary ones that most people are familiar with. We've seen more movement in the last 10, 20 years to low distortion projections. And Wisconsin was one of the very first states to come up with county coordinate systems back about almost 30 years ago now. As the counties were starting to work with GIS systems, they really didn't want to work in state plane coordinate because the coordinates are so huge. They wanted something that was closer to, more manageable coordinate-wise, and gave them something that brought the Earth measurements, or physical measurements, closer to the grid measurements. Because 1 in 10,000 just didn't cut it. I mean, that wasn't accurate enough. People would always be saying, "Well, I measured this distance on the ground, but it doesn't match what's in your GIS." Well, the GIS is in the grid system, and what you're measuring is in a ground system. There's enough of a difference in between them that threw people for a loop. So the idea was to minimize the distortions by bringing that grid closer to the ground. Remember, the smaller the area that you're working with, the less your distortions are going to be. You're not going to eliminate them entirely, but you're going to minimize them and make them much smaller. So instead of looking at the entire state as a coordinate system, or as the state in 3 different coordinate systems, they looked at each county in its own coordinate system and designed a grid, or designed a low distortion projection for that particular county. And in Wisconsin, the criteria that they had for the maximum distortion from ground to grid, not from ellipsoid to grid, was 1 in 50,000 in the urban areas and 1 in 30,000 in the rural areas. And because of the sizes of the coordinate systems and the way they designed them, they met that. I mean, it was routinely 1 in 100,000 difference, ground to grid and that type of thing. So essentially, ground and grid are the same thing. That's the nice thing about low distortion grid systems. The bad thing about them is we have 58 zones in Wisconsin. We got a lot of coordinate systems in Wisconsin. And those did not exist on NAD 27. Those were developed on NAD 83 and have been since updated in that. But Wisconsin's not the only one that's done that. Minnesota also has low distortion projection systems. Now, it doesn't show Illinois on here, but they just developed theirs, or they're in the process of developing theirs. Oregon's interesting. Is anybody here from Oregon tonight? I didn't see Oregon in the list of stuff. Oregon, when I did some presentations for the Blue Mountain chapter up there, and one of the things I did was talking about coordinate systems. And I looked at theirs, and they've got all their systems overlap each other. You can have a point that's in as many as 3 different low distortion projection systems, depending on the area that you're working in. So it's a little confusing. Um, but they do have those, and there are other scattered ones throughout, and there might be other states that develop them on here. Now, one of the things that NGS came out with when they were looking at developing the new datum is they contacted all the states or representative organizations within the states and said, look, this is what we're going to do. You're going to have a statewide system, you're going to have a state plane coordinate system, and you can have a couple of low distortion projection systems. Okay. But it was like a choice thing. It was like a la carte. You could pick anything you want. It was basically you had a choice of things that you could do. And we came back at them right away from Wisconsin and said, look, we got to have a county system for each county. They said, we can't do it. We can't do it. That's just too many things for us to handle. I said, well, all of our counties have got their GIS systems invested in those coordinate systems. The last thing we've got to do is to uproot all that and start all over again with new coordinate systems. So we went round and around with them, and finally they said, okay, for Wisconsin, at least, we're going to allow the counties to come in as low distortion projection systems. We told them basically you can keep your state plane coordinates. Nobody uses those here. And a statewide system, only the DNR uses that here. Everybody else uses county coordinates here. So that's what we've done. But any of the states that got active with NGS when the call came out could have LDPs adopted. And there's an advantage to that, a couple of advantages to that. One is right now in Wisconsin, we have to manage those coordinate systems on our own. Okay, there is no other authority that handles those things. So we handle it basically on our own. Once it becomes adopted as part of the new datum, then NGS handles them. And right now, we don't have, it's not part of any of the NGS software. So you can't convert any positions that are in state plane or UTM using NGS software into our county coordinate systems because they're not supported by NGS. Under the new datum, they will be adopted and supported by NGS. So then there'll be transparent conversion of coordinates between all these different systems, including the county systems. Now, I don't know how active you got individually in your own states and what you've got in the works for it and stuff like that. But that was one of the things we pushed for. And Minnesota did also, and so did Illinois because they're developing theirs. I think Iowa got in on it also. So I don't know how actively that's been going on in other states or not. But that's the opportunity. Most states will have some sort of LDPs when a new datum is adopted, and it will be supported then by NGS, just like state plane and UTM is now. Anyway, all right, so let's talk about ground and grid. You get my little graphic here, ground beef with the grill marks on it for the grid. Okay. You know the joke is bad when you have to explain it. All right, remember there's 2 types of distortions. There's a distance distortion and there's a direction distortion. The distance distortion, we can compensate for it or do the actual grid, ground to grid in 2 steps. The first step is to go from ground to the ellipsoid. And the way we do that is through those heights. Remember that height relationship between the Earth, the ellipsoid, and the geoid and all that? Basically, we go through from the ground, our horizontal distance measurement at the ground, down through our orthometric height and our geoid height to get to the ellipsoid. So we go from ground to geodetic. And we do that using something we call the elevation factor. And the elevation factor is simply a proportion. It's a proportion of the radius of the Earth divided by the radius of the Earth plus the geoid height, or plus the orthometric height of the line plus the geoid height. And that's referred to generically as the elevation factor. So if you take the horizontal distance and multiply by the elevation factor, that gives us the ellipsoidal distance or the geodetic distance on the geoid. Excuse me. Now, that's regardless of whichever grid system that you're using. We're not even talking about grids here. We haven't fit state plane or UTM or anything to that here yet. We're just going from the ground to the ellipsoid. So every reduction for every coordinate system will involve this particular step right here, ground to ellipsoid. Now remember in NAD 27, when we fit that to Meads Ranch in Kansas, this didn't exist. The geoid height didn't exist. So basically, we just used the elevation, the orthometric height of the point, and reduced that to the geoid or to the ellipsoid directly, to the height, the orthometric height of the line. Okay, so we got to have the height of the line, which we generally use as an average of the endpoints, and we have to have the geoid height, and we have to have a radius of the Earth. And we can use an approximation of 2902.00 feet or 6,371,000 meters. Now remember, the ellipsoid is, ellipsoidal. It's not circular. So these are approximations, but they're pretty good approximations for most calculations. You can come up with more accurate radii using the radius and the azimuth, but it's a more complicated process. It generally doesn't give you much better distances. The next step is to go from the ellipsoid to the grid. Now we pick a grid, whether it's UTM, state plane, or low distortion projection or whatever. We fit that grid to the ellipsoid, and then we relate one to the other through that scale factor, that grid scale factor. Remember the one that is constant east-west in a Lambert con, constant north-south on transverse Mercator. So we just multiply the ellipsoidal distance times that scale factor to get it into the grid system. So that's
Jerry,
what makes it unique. Yes, sir. Yeah.
Jeremiah's got a question. Sorry,
Sure.
I was trying to chime in, but I was muted myself. So go for it, Jeremiah.
Well, I've got a question about this conversion. I mean, we're talking about the lines, lines being 2 points, one on each side of the line. Is there a single factor that you're calculating, or are you calculating that conversion factor for each vertex on that line and then averaging it out? I mean, because
that leads to another thing I'm going to get at in just a little bit here. But normally what we do is we use the average of the endpoint elevations.
Okay, so it's an average.
Yeah, because technically, if you have the distance at one point that's at a lower elevation, that's a different distance than if you have the distance at the higher point because of the convergence of the vertical lines. Now, if you're working with the total station is a good example of this. In your total station, you can set it to correct for Earth curvature and refraction. And that will compensate for some of this stuff here, and it'll actually come up with an elevate distances based on an overall average of that type of stuff. So that's why we use an average elevation, okay, here and here. Now, if you're working in relatively flat terrain, okay, it's not going to make much difference. It's when you're really working in distances that have got tremendous elevation variations one end to the other, that, yeah, you're going to have some effect on that. That's why we use the average. But again, I'll talk about that in just a second here when we talk about project-based reductions. Does that get your question answered, or?
Well, yeah, because you know, if you just think about the measurements that we take, we're connecting dots.
Yeah.
And almost none of our measurements are directly north or directly east.
Right.
They're all on a weird angle. So
well, yeah,
almost,
it depends on how much calculating you want to do. I'll talk about that also, because and the ellipsoid makes it even more interesting because of the fact that it's not a constant radius. Okay. If we want to really nitpick, the other thing we can say is we go back to this diagram here when we go from here to here. This is a chord distance. This is actually an arc distance because it's on the ellipsoid. But we're using a chord distance to approximate that. And I don't have the calculations here, but I did some calculation once to see in Wisconsin typically how long a distances would have to be before this was a significant difference between these two based on the flatness of the ellipsoid. And it was like miles and miles and miles. But so we're making some assumptions in here also. Okay. But again, we can compute that and come up with a better radius and make this an even better distance. It just depends on how much calculating you want to do and how much of it is really necessary for the accuracy of the survey that you're doing. So like in my legal classes, the answer is it depends. But anyway, so and sometimes what you'll see will happen is if you're working in a coordinate system, you'll see what's referred to as a combined factor, which is just the elevation factor multiplied by the scale factor, and you do it all in one shot. Okay. Now, to kind of, I don't know, and with the low distortion projection, that projection is very close to the surface, so that combined factor is going to be very close to 1. Okay, so that distortion is going to be minimized. So again, whatever we shoot for our distance, we can use that as a grid distance as well as a ground distance. Okay. In most cases, usually what I suggest people do is if there is a terrain variation, pick out your worst situation and see if it makes a difference there. If it doesn't make a difference there, it's not going to affect any of the rest of your survey. You know, so it's like a worst case scenario thing. Convergence, real simple. That's a function of longitude. If we know where we are longitudinally in our projection, we know we can figure out what our convergence is. Then we just we subtract convergence from the geodetic azimuth to get the grid azimuth. Bang, add, multiply, piece of cake. Now, we look at this, we got to have n. We can get h off a topo quad if we haven't run elevations and stuff through there. But n, you can't just pick that off a topo quad or something. That's a geoid height. And the same thing with convergence. You can't just pick that off a topo quad. That's a function of the geometry of the surface of the coordinate system that you're in. So where do we get stuff like that? Well, a couple of different places that we can pull stuff out. And one is the Geodetic toolkit on the NGS website. If you've not used that, you should go there and get familiarized with NCAT, because NCAT is going to be the tool that when the new datum comes in, all of our LDPs are going to be on. Right now, it supports UTM, state plane coordinate, the national grid, the Earth Center one, all that kind of stuff. More of the regional ones. So that if you've got geodetic and you want state plane coordinates, you just put in your latitude and longitude and run it through, and it'll generate a bunch of stuff for you, including the convergence and the scale factor that you'll need. Okay. It doesn't give you the geoid height, but then they have another product called Geoid X. I put in XX. The latest version is Geoid 18. That's a geoid model that most of you are using in your GPS stuff anyway. When you're doing your GPSing and stuff to convert your ellipsoidal heights to orthometric heights, you have to have a geoid model loaded. Well, Geoid 18 is the latest one that NGS has developed. That's the one that most people use. But it's also an interactive calculation on their website in their Geodetic toolkit. So if you put in the latitude and longitude in it, it'll come back to you with the geoid height in that area. And again, the ortho heights can come from USGS topo quads. And again, remember, when NCAT, when the new datum comes through, NCAT's going to support all the other LDPs and stuff in there. So you'll have additional lists to pick from in here. So start getting used. If you're not using it, it's a pretty neat little package to use to generate some information for you. And again, it can do conversions between datums also, transformations between datums. But remember, that's not an exact science. There's going to be some error introduced in those positions. The other place that you can get them is off our good old friend, the data sheet. And if you explore the data sheet a little bit, you'll find additional information on it that you may not have been aware of or just never used. This is Point Jerry for my namesake, my control point that's in the NRS database. It's a horizontal control point. So you see that it's got its NAD 83 2001 position, and it gives it the 5 decimal places, and it says adjusted over here. So that tells you that it was adjusted as part of the NAD 83 2011 network. So that's in the latest realization of that data. If you look down here, you'll see NAVD 88 ortho height, and it shows it to the nearest tenth of a meter and the nearest foot. And at the end here, it says vertcon. Now, this is not a benchmark, but they do have an elevation in here, but it's an approximate elevation. And it says vertcon over in here because that's a program called vertical conversion. What it had in here initially, this is NAVD 88, which is the current vertical datum, and NGVD 27 was a previous one. So what they did is they had interpolated the elevation for the position off of a topo quad, and then ran it through vertcon to convert it to the new one. So that's not a benchmark. I wouldn't use that for elevation control, but I can use that for my height and my elevation factor. Down here, it shows me my geoid height for that point. Where did it come from? Geoid 18. It's a geoid model that was used for that. Down below that, further down on the data sheet, you'll see the control in terms of rectangular coordinates. This point is known in the Wisconsin South State Plane Coordinate Zone, as well as UTM Zone 16. And it's in here twice in the South Zone, once in meters, and the other in terms of survey feet. You can see the coordinates are really big for the east coordinate, 2 million for the coordinate. That's kind of cumbersome to work with. And it's got the scale factor and the convergence. And you notice that the scale factor is different for the state plane coordinate system than it is for the UTM system. Two different grids, they're fit differently. Okay? You see that the convergence is quite different. Okay, 11 minutes in the state plane coordinate system. Our central meridian for the state plane coordinate systems is at 90 degrees. And you can see that Jerry is pretty close to 90 degrees longitude. Okay? So the convergence isn't very large. But we're at 90 degrees is where two UTM zones meet up. One's at 87 degrees and the other one's at 93 degrees. So I'm on the edge of one of those UTM zones, so you can see that that's a relatively large convergence because I'm towards the edge of the zone. So that's why they're different. Okay? So the scale factors and the convergences are different. That's the fitting of the grid system to the ellipsoid. Down below here, it shows elevation factor times scale factor equals combined factor. So basically what they did is for the state plane, they took the scale factor and multiplied it by the elevation factor, this thing here, to get the combined factor. But that's at Jerry's elevation. That's at this elevation right here. Again, if my next point is lower or considerably higher, that might not be a good elevation factor to use, but that's at point Jerry. Okay? So normally we figure out our own elevation factors based on the elevations of the points, as opposed to working with just one like that that's based on a single control point, which may or may even be part of the survey. All of the, I'm pretty sure that except maybe up in Alaska, all of our geoid heights are going to be negative, which indicates that the geoid is actually below the ellipsoid. The ellipsoid is above in that case. So we're going downward from the ellipsoid to get to the geoid. Now, this kind of ties back to the previous question, as well as what I was just talking about, is the elevation factor. If we're working with a small area, and generally over most areas, n doesn't change very much. It may change in a hundredth of a meter or maybe even tenth of a meter, but generally it doesn't change very much. So you can generally use one n for the entire project area. The terrain, however, can have an impact on that. So rather than, I mean, you could use Jerry's. So right here, we can use the combined factor at point Jerry for the state plane coordinate calculations. But if I'm going to be working even on just section lines and stuff in there, there's enough terrain variation in that area that this elevation factor is going to vary. So what we normally do is we compute an average for each line. Now, this is also important, and now working on another paper dealing with proportionate measurement and that type of thing. One of the differences when we talk about doing proportionate measurement for the corner restoration, we're proportioning a contemporary measurement against a record measurement. Okay. Now, today it's common that we're doing that contemporary measurement. It's between the two corners, say a quarter corner and section corner, or two section corners. So we're basically shooting one line at an average elevation across there. But when they did it originally, they did it with a chain that was 33 or 66 feet long. In some cases, they had lower elevations. In some cases, they had higher elevations, lower, higher. They had combinations of stuff. And when you're really proportioning today against record, you're actually comparing different measurement methodologies because of the fact that you're working with a uniform elevation versus broken up into smaller elevations. I haven't figured that one all out yet, but it's one that I'm kind of wrestling with because, hell, I can't be retired. But anyway, so we normally take, and it's easy enough to grab an elevation for each point off of a topo quad and just use an average elevation for each line. Grid scale, same thing. Remember, it varies east-west, constant north-south on a Mercator projection, east-west. It's not constant throughout the air. So if you've got a long linear project like the DOT does when they're doing highway work, they can't use one scale factor for that entire project. So what they'll normally do is break it up into regions and then have a scale factor for each one of those regions. And then match them all up together and that type of thing. So you can figure out what these scale factors are by running approximate latitude and longitude with NCAT, and just get that through there, and it'll give you the scale factors that you work with. And you don't have to be good to nearest 5 decimal places on the seconds to get a good scale factor. You just have to have it in there within a couple of minutes, and that's good enough. Let's look at an example of how we pull some of this stuff together and the kind of effect it has. This is north quarter line, the northwest quarter of section 34 in Dane County, Wisconsin. Dane County, Wisconsin. And I've got a northwest corner and I got a north quarter corner. And we shot the distance, got 2638.25 feet and an azimuth or a bearing of north 80 at 1134 east. Let's say that's the geodetic geodetic bearing for that guy. So what we want to do is we want to determine the Wisconsin state plane coordinate south zone grid distance and bearing between those 2 points. Now from the topo quad, we can pull their elevations. 960 at the NW at the northwest point, and 1050 at the north quarter corner. And the approximate position of the northwest corner, we can pull that off the topo quad also, 4257.5 minutes, 89 degrees, 39 3/4 for the longitude. So we can use that information, run it through NCAT, and that'll tell us what the scale factor is for the state plane coordinate at that location and what the convergence is. And then if we run it through Geoid 18, it tells us what the geoid height is at that point, negative 34.046 meters. And we basically have the information that we need now to go ahead and start reducing this stuff. We know that we're going to use a radius of 2902 for the radius, and we'll use the average elevation, stick it into our elevation factor equation. And I put this in there as an intermediate step just to show you what it looks like, but this is the elevation factor, 0.999957264. So if I multiply that by my ground distance, that gives me a geoid distance or ellipsoid distance of 2638.137 feet. Now, one thing that you got to remember to do is it gives you the geoid height in meters coming out of Geoid 83, Geoid 18. You have to convert that to feet. Otherwise, you'll introduce an error in this equation if you're working with feet with all the other stuff. My scale factor, 0.9962224, that's how to get from the ellipsoid to the grid. If I multiply that by this, that gives me 2638.037 feet for my grid distance. If I compare the two, here's my ground distance, 2638.25. Here's my grid distance, 2638.037. It's a difference of 2/100ths of a foot, or 2/10ths of a foot. And that works out to a distortion of 1 in 12,000. So I wouldn't use my ground distance as my grid distance. That's too much of a distortion. I can measure, I can guess better than that. Okay? So that's we're not going to treat ground as grid in this case here. To get my direction, to change my geodetic to a grid direction, now I like to work in azimuths because with an azimuth, it's a continuous clockwise angle, and I can either add or subtract my convergence to the azimuth to get the converted value. If I'm working with bearings, depending on which quadrant I'm in, I have to either add it or subtract it, and rather than try to do that, I just put it in terms of azimuths. So my azimuth, my geodetic azimuth for that guy is 88 degrees 11 minutes 34 minutes because I'm in the northeast quadrant. I subtract from it my convergence that I got coming out of NCAT. That tells me my grid azimuth is 8757.39. Convert it to bearing, and that's north 8757.39. That's all there's to it. As long as I can get the pieces that I need for it. Okay. Now, when we talk about low distortion projections, are there any questions on that? I mean, I went through that quick, but it's pretty straightforward. It's all systematic. Okay. And a lot of times your software does that for you. And in some software packages, I know that when you set it up, you give it a coordinate system. You can tell it an average scale factor or an average elevation factor to use and all that kind of stuff. If you can avoid that, avoid it. Let it generate for you based on positions and that type of thing. For one thing, we got this. Let me go back. This guy right here, this 13 minutes, 54.8 seconds. That's the grid. That's the convergence at this point here. Is the convergence at the north quarter corner going to be the same?
No way.
No, it won't. Grid north are going to be parallel there, but geodetic north isn't going to be, right? The grid direction in this direction from the northwest to north quarter is going to be exactly 180 different than the grid direction in the other way, right? But the geodetic direction is going to be different because of the convergence of meridians. And you'll see that if you put in the approximate coordinates of this guy, geodetic coordinates of this guy here in the NCAT, you get a slightly different convergence. If you're working with a northwest corner and a west quarter corner, you'll see that the convergence are going to be pretty close to each other because they're north-south of each other. Okay, but whenever you got that east-west separation, you're going to get different ones. Now, what does true mean bearing mean in BLM work?
Cardinal.
Well, cardinal, but cardinal where?
Right. Yeah.
Because remember, cardinal is true direction, right? So the true direction at one end of the line is going to be different than the true direction at the other end of the line. And what you're supposed to use when you're doing cardinal equivalence is to use a true mean bearing, which is at the middle of the line. Okay. So theoretically, it's the average of this one here and this one here, those two right there. But if these points are far enough apart, and this is where things get really fun to work with ellipsoids, is the convergence at the center of the line is not half the convergence at the endpoints because you don't have a nice circular surface, you have an ellipsoidal surface. Yeah. So things can get real flaky real fast.
Yeah. And Jerry, before you moved on, you had questions, and it was, would the conversions be U.S. survey foot or international foot?
We use survey foot here in Wisconsin. Okay. So I'm doing everything in here that I'm dealing with in feet are in survey feet. Okay. I know that some other states, Oregon, I was surprised when I did stuff for them that they use the international foot.
Yep.
But for things like elevations, it may not make a difference, but for coordinates, it does. 1 in 500,000 is the difference between the two. So you got to be careful which one you're using and make sure you're using the one that's jurisdictional, that's jurisdictionally defined for your area. And with NAD, with the new datums, what's going to happen to the survey foot?
Well, we'll
It's
still
going to,
have to use it for retracements, but they're not publishing coordinates in survey feed
yeah,
anymore.
basically they're saying it's going to go away. So there isn't going to be, because right now the way in Wisconsin it doesn't really say it's a survey foot. It says it's the way it's defined in NGS circular number such and such, and in that circular it defines what the survey foot is. Well, all they got to do is change that definition with the new datum in that circular, and all of a sudden ours gets updated. Okay. So again, you got to be careful and make sure that, yeah, and like the comment was, it may not exist from that point going forward, but it will exist from that point going backwards. Okay. So you still need to be able to work between the different systems when you're doing retracements and that type of thing, particularly where coordinates are involved. All right, let's see, what was I at? Old distortion projections. Oh yeah, here's a picture of the one that's in Oregon. You can see all these overlapping systems. They don't like just butt up based on jurisdictional type. They design them based on major geographic or major elevation type of areas, I guess, from what they had. So it's interesting. Like you got this whole big long narrow one that's in the coastal area because that's the lower area. But then up in the mountains you have different little, and you can see they're overlapping. One point can mean a whole bunch of different coordinate systems. But those aren't supported by NCAT. So how do you get the information that you need? Now you can still get the geoid height n because that's independent of the projection. That's the geoid model. So as long as you can give it a rough latitude and longitude, you can get the geoid height. But how do you get convergence and how do you get scale? Some states, like I say, have software, some software that you get, some mapping software, you can generate that information, or some GIS software. One of the things, because we maintained our own coordinate system in Wisconsin, we didn't have that kind of software. So I finally got around. I wrote one about 5 years ago. And this is a system this is a Concord that does all the formal coordinate systems in Wisconsin on a single datum. So you can feed into it Geodetic, State Plane, UTM. We have a Wisconsin transverse Mercator, and we got the county coordinate systems, and you can convert to any other systems and generate the coordinates and the convergence and the scale factor for that. And you can do it point by point or for the entire file. But the thing is, you have to have something that allows you to compute that kind of stuff. And in Wisconsin, this is the product that we have for it.
10
All right, so let's
decimals,
look.
my calculator is going to blow up with 10 decimals.
Well, it used to be, hey, you talk about decimals. When we talk about state plane coordinates, back when calculators first came out, they couldn't display all the digits for a state plane coordinate. Okay. Now, internally, they carried more digits than they displayed, so you got really creative. You put in the decimal part first, and then added to that the mantissa part, and it would shove it off the display, but it would still be inside the calculator. But it was a hassle to work with stapling coordinates when you couldn't display them all on the calculator display. All right. Okay, for the same example that I did before, for the northwest quarter to the north quarter corner, where I reduced that to the state plane system, let's look at the effect of reducing it to the Dane County coordinate system, which is our low distortion projection for Dane County. Now, from the topo that stuff, all this other stuff is still the same. Radius is still the same. Geoid height is still the same. The only thing that's different now is we're dealing with the low distortion projection. So I had to run these approximations through Concord to get the scale factor and the convergence at that point. So you see my scale factor is really, really close to 1, which is what I want it to be, in combination with the elevation factor to make sure that that distance is pretty close to the ground distance. So when I do my distance reduction, the only thing that changes here, remember, in here, nothing changes really, because this is going from the ground to the ellipsoid. That's irregardless of the grid factor or the grid that's used. If I take that and I multiply it by my scale factor to get my combined factor, see, I'm getting really close to 1. And when I multiply my ground distance times that, I get 2638.23 compared to 2638.25. There's a difference of 2/100 of a foot. And that translates into a distortion of 1 in 131,000. So am I going to treat ground distance like grid distance? Sure, for all intents and purposes, they're the same. So I would look, if I'm working on a project area, I'm going to look at which is my longest line with the biggest elevation differences, and which is my worst case situation. And I'm going to compute for that line there. And if I get 1 in 131,000, it doesn't make a difference for that line. It's not going to make a difference for any other line either. Okay. So that's what you look at your, so you can see it makes sense to have a low distortion projection for that area. Now that's Dane County. If I were to go outside of Dane County 20, 30 miles or so and keep extending that coordinate system out there, then my distortions are going to get considerably bigger. But then I'm exceeding the area of my interest. Okay, so I just want to stick to the middle of my tomato. That's what the Dane County coordinate system is. That's the middle of my tomato. Yeah. My convergence is still 9 minutes. So I'm not going to ignore that, but because it's a small area, that 9 minutes is pretty consistent throughout my project area. It's not going to vary as much as my convergence does for my state plane, which goes all the way across the state. This only goes across Dane County, which is 1, 2, 3, 4, 6 townships wide. So it's only 36 miles wide. Okay, so it's not, doesn't have big of an effect on there. So to kind of summarize the differences between, here's my ground distance, state plane, whiskers system, like Dane County coordinate system. You can see it's very close. There is a difference of almost 10 minutes on the convergence, but that's pretty consistent throughout part of the county. So there's an advantage to using my low distortion projection system. Okay. Now, how about going the other way? Say that I've got grid and I want ground. Well, basically what we do is we go backwards. So here are the northwest and southwest corners of section 23 of the Wilmette meridian in Oregon. And I've got state plane coordinates, Oregon North Zone state plane coordinates for these 2 points here. And I want to say, well, I can get my grid distance from that, my grid direction, but what's my geodetic direction and my ground length from that? So I just work it backwards. Okay? So I run it through NCAT to get my information that I need. And in this case here, because it's a little bit along the line, I'm going to go with convergence at both ends. Now you see that my convergence, this is a north-south line, pretty close to a north-south line. My convergence doesn't change very much between those 2 points because convergence is a function of east-west. My scale factor, however, does change out in this area here. My geoid height only changes by 0.01 meters, or 0.0, no, that's supposed to be meters, not feet. 0.01 meters going from between those 2 points. So it doesn't vary much, even in the more mountainous type or in the higher elevations than that. And again, I'm working in international feet in Oregon. So basically, if I do my inverse calculations, I get from my grid distance in international feet and my grid bearing, okay? Now I want to work backwards, and I'm going to use my average scale factor. And since it was the grid is equal to the elevation time, since I wanted to get the ground distance is equal to the ellipsoidal distance times k, work this way backward. Basically, if I take that grid distance divide it by the scale factor, that gives me the ellipsoidal distance. So I'm working backwards. Then if I compute the inverse of my elevation factor and run that backwards, I get my ground distance, 5144.958. And for my grid direction, my geodetic direction, I'll take the grid azimuth, I'll subtract my convergence from that, 2 degrees, I'm at the extreme, and that's my my geodetic direction. So it's basically just reversing my calculation process. It's not difficult, it just takes a little while to work back and forth on that stuff. Or you can automate it in the software, kind of depending on the software that you use it. All right, let's throw one more thing in here. I got a couple more minutes, and I'm going to kind of throw this in here just to bend your mind a little bit more. Okay. Geodetic and true. Now, you notice that I've been sticking to using geodetic and not really saying true, except when I talk about, the public land survey system. If you look at the manual surveying instructions of 2009, it says the direction of each line of the public land surveys is determined with reference to the true meridian as defined by the axis of the Earth's rotation. The true meridian is a line along a meridian of longitude. Historically, determination of the true meridian has been based upon direct astronomical observation at the point of record, and thus an astronomical meridian. So basically, they're saying the way they used to determine true meridian is how? They do a solar observation, right? They do a solar observation, or sometimes later on they would do a Polaris observation. But that was what kind of revolutionized things. When William Burt developed the Burt solar compass, he made the determination of the meridian a lot faster and more accurate, because actually what happens is is if you ever done any astronomical calculations, it's a pain in the butt. But the Burt solar compass mechanically solves that problem through the arcs and stuff that it has on it. So basically, you're doing an astronomical observation to determine true meridian. So what they're saying here is that the true meridian is equated to the astronomical meridian. So it says the value of the angular difference between astronomical and geodetic meridian caused by the deflection of the vertical relates astronomical meridian to the geodetic meridian. Remember the deflection of the vertical? That's that skewness of the ellipsoid and the geoid. Now, in a 1979 man, the one that preceded this one, this isn't in there. Nothing in there is about the deflection of the vertical. And that's because the datum at that time was the 27 datum. And the 27 datum, remember, the geoid and the ellipsoid coincided. There was no deflection of the vertical. But under 83, they're separated, and there is. So what they're saying is you actually would have to correct for the element of the components of the deflection of the vertical to convert a geodetic meridian to a true meridian. Hot damn. Well, how will you do that? Well, I'm trying to come up with a diagram to let you kind of visualize what's going on here. But say we're sitting here with our instrument and we have our vertical line there, okay, that would correspond to our plumb line hanging. That's the direction of gravity. That's perpendicular to the geoid. The ellipsoid normal is a line that's perpendicular to the ellipsoid at that position. The angle between those two is that deflection in the vertical. Now, that's in whatever orientation, depending on how those surfaces are related to each other. But you can break that into a north-south and an east-west component. So you have this component east-west direction, and this component north-south direction. The one in the east-west direction affects where the meridians are with respect to each other. Okay? And if we kind of look at this now, this is, you got to visualize this in 3 dimensions. Here we are sitting on the Earth. Here's our geoid down here. Our vertical line is perpendicular to that geoid and extends down to the ellipsoid and is perpendicular to the astronomic north. Our component of the deflection of the vertical projects down through here, intersects down here at the ellipsoid, and that defines geodetic north. So if there is no deflection of the vertical, these two coincide. If there is a deflection of the vertical, there's a slight angle between those two. And that's called the Laplace correction. That's equal to this component times the tangent of the geodetic latitude of the point. Okay. So the Laplace correction is added to the astronomic well, actually take the Laplace correction, subtract it from the geodetic to get the astronomic. How big is that puppy? And is it worth calculating? Well, if you go to Point Jerry, down at the bottom, and we're looking at all this other stuff down here, we see Laplace correction, minus 0.36 seconds. It's not very much, is it? Just a slight, because there's not very much of a deflection of the vertical there. Where does that come from? There's a program in a geodetic toolkit called Deflect 18. That's based on the Geoid model, Geoid 18. So every time Geoid 18 gets updated, so does Deflect 18 gets updated. So you say at 0.36 seconds, that's not, I can afford to ignore that. Okay, here's Point Monroe, which isn't very much further away from it. This is less than 20 miles away from Point Jerry, and it's got a Laplace correction of 8.73 seconds. Okay, can I ignore that? Well, at the end of a 1 mile line, at the end of a section line, it places the end of that section line almost a quarter of a foot, which is enough to create what we call pincushions, right? Okay. So yeah, that one we might have to compensate for. So when you look at stuff like that, because that's put in the manual, you really have to take a look at that and see, is that something that I need to be concerned with when I'm doing, say, proportionate measurement, corner restoration by proportionate methods? Because when I talk about going into my cardinal equivalence, that's based on true north. And if I'm 8 seconds off in a 1 mile line, that can throw my proportion off enough that it introduces error into my position. Where I just saw somewhere on LinkedIn or wherever it was, there was two BLM monuments next to each other, and somebody said, why would somebody put the BLM put two monuments next to each other? You know, those two monuments are within 0.22 feet of each other. You know, that could be the difference between an application of the Laplace equation or not applying it. Where do you get it from? Again, Deflect 18 is a software program that you can run online. Put in latitude and longitude, and it'll generate for you a bunch of stuff in there that they don't do a really good job of explaining. But the horizontal lap, that's Laplace correction right there at the end, minus 6.51. This is at somewhere out west. I just put in a 45-degree latitude and a 103-degree longitude just to see what it would be. But it's amazing how much this can change over a relatively small area. You can get quite a bit of difference. But that's, again, based on that geoid model. So you always want to check that just to be sure that it is or is not significant. So remember, your proportion is based on a true meridian, and you got to decide whether you want to apply the Laplace correction or not. Okay, so that's just one more thing to worry about. Okay, so we kind of ran through this stuff real quick here. Are there any questions flowing around over here in chat that?
No, you're caught up. Yeah, we're caught up on the chat.
Yeah, I'm just looking to see if there's any. All right, well, let me throw up my homework screen, if I can find it, and see if anybody can answer the questions that I had on there. There we go. Is it showing up? Do you see it on the screen?
Yep, you're good now.
Okay. What are the two distortions going from a 3D Earth model to a 2D grid system? This is where you jump in with the answers because this is positive feedback now. It's just like being back in teaching. It's like I never left.
That's right. Nobody's responding.
What kind of calculation we just did? We did direction and we did distance, right? Those are two distortions, directions and distances. What's deflection of the vertical?
Oh, George has
How
got
could
his
you
hand up.
forget?
George has
Hey,
got his
who
hand
wants
up.
to count for
The
CE?
angle,
Yeah.
Uh, I've got my hand up, but it's to tell a horror story from back in the day that most of these younger surveyors won't understand. If anyone's interested in it, I'm happy to share it.
We'll do it after his homework then. Yeah.
Yeah.
That's awesome.
Sounds good.
Okay, everybody got an answer for the deflection of the vertical?
the angle between the normal to the geoid and the normal to the
Right,
ellipsoid.
yeah. Basically, it's how parallel the two surfaces are with respect to each other. Right.
Nice.
What's the maximum ellipsoid to grid distortion for the following system? State plane? Remember what it is?
2100.
What's that?
1 to 10,000.
1 in 10,000. Very good. How about for UTM?
1 in 2,500.
1 in 2,500. There you go. What are the types of projection surfaces used for state plane coordinate systems? We got two of them. We're also called developable surfaces.
Lambert, Conic, Traverse, Mercator.
Right, yeah. And you'll also see reference to an oblique Mercator. That's
Yeah.
used like on the panhandle of Alaska because they kind of got rotated about 40 degrees because of the way the panhandle is oriented. What NGS product can be used to convert coordinates between different systems?
NCAT.
NCAT, okay, which if I remember quick stands for NGS Coordinate Conversion and Transformation, I think is what the acronym stands for. What is the Laplace correction? Last thing I talked about. Angle between what and
Going
what?
from geodetic to
Geodetic
astronomic.
North.
Yeah, geodetic north and astronomic north are the correction that you apply because of what it says in the 2009 manual about how true meridians were measured. True or false, a state plane grid distance will always be shorter than its horizontal counterpart. The key word in there is always.
Yeah.
False.
It could be
Yeah,
both.
false. Just
It can be either
based on
way, right?
elevation. Yeah.
Depends on where the ground is with respect to the grid, right? When you're down in Death Valley, I suspect that those are going to be lower than the grid system is, so the distances will be short, be longer on the grid. What forces define the geoid?
Gravity and distribution of Earth's mass.
Gravity and what? Say?
The Earth's mass.
Well, Earth's mass is the gravity is affected by the
Okay.
Earth's mass, right?
Surface. Earth
Rotation.
surface.
Rotation.
Rotation.
Spinning of the Earth, right? And you get all sorts of other stuff like the wobbling of the Earth and the shifting. It's all sorts of strange stuff. Grid scale on the UTM projection varies east-west.
False.
Okay, I'll give you another guess.
True.
Should be
Yes.
true because
Yes, it does.
it's going east-west versus north-south.
Yeah, north-south, Wisconsin, east-west, it varies.
Yeah.
Okay, and then the other ones here are computational ones, except for the very last one. You can try going through these. And again, some of these are just using the NCAT, the Geoid 18, and all that kind of stuff. Go through those, just to kind of familiarize yourself with that software. You have not played with it. True or false? Geodetic meridians are parallel. Oh, come on.
Oh,
I'd say true.
Yeah.
Yeah, true.
No, it's not true. Not geodetic meridian. Grid meridians are parallel.
Yeah.
Geodetic meridians all converge. They're on the ellipsoid, and they all converge
Yeah.
to the North Pole and to the South Pole. Okay. The only ones that don't converge are grid meridians. Even magnetic ones converge, even though it's not uniform and straight. Everything converges to some sort of pole except for grid meridians. Okay,
Love it.
that's all I got. If you have any questions, or you try to figure out in your software how some of this stuff happens in the particular software package you got, I'm more than willing to answer any questions that you have on this stuff. Otherwise, that's all I got. Unless George wants to tell his story, we still got maybe another 3 or 4 minutes here.
That's right.
Can you tell it that quick, George?
Sure.
All right, go for it.
Back in the early 70s, I was on a field crew as a crew chief, actually, working for a company that had offices in Nevada and California. Their main office was in Sacramento. We were working on a job in the Carson Range at about 7,000 feet elevation. And the subdivision that we were laying out was calculated and platted by the Sacramento office. They did all the mapping on grid. So as a surveyor on that project, we had to take every dimension on that plat and convert it to ground. We had to correct for slope. We had to correct for temperature and pressure. And then we had to brush the lines to the doggone timber. It was hell keeping track of all those corrections that we had to do. And there was no real reason for it, really. To complete the story, I went back the following fall. We were doing that job in the fall, late summer, early fall, and early winter. I went back the next fall to lay out a couple of corners and check on them. And I was looking for the brush line that I knew we ran on that survey when we did it. And we did eventually find the brush line. It was about 8 feet off the ground. That's how much snow was on the ground. But just so people know, we didn't always have all these amazing tools that we do now, computers and software and stuff to do this work. We had to do this stuff with a set of trig tables and an idea of what the correction was per 100 feet. It was fun. It was fun. Surveying was different then. I hate to say it's easier now. It's more complicated now, but I think we have more tools.
Yeah, it's a different challenge now. And that's one of the reasons that stapling coordinates weren't really popular initially, or weren't popular from the 30s all the way up through the 70s, was they were just too cumbersome to work with the computing tools that we had at that time. And it wasn't until we started getting into more capable calculators and in particular computers that we started to be able to work with that kind of stuff. Even now, this will throw you through. Southeastern Wisconsin Regional Planning Commission, which consists of 7-county area right around Milwaukee, they still do a lot of their work on NAD 27. And that's because the guy that was in charge of that, Kurt Bauer, was a diehard anti-NAD 83 when it first came out, because they did everything, they remonumented everything and did it all on NAD 27, and there was no exact conversion factor going from 27 to 83. And on top of that, they were one of the earliest ones to get into GIS in a big way, and they had a little symbol that they had for their area sewer pack. They had a colored in part of, and the way they created that, this is before they had libraries, they took a digitizer and they actually shaded it in with the digitizer going back and forth. So they had coordinates on every single one of those damn points in that symbol. So in order to convert their GIS over, they would have to transform all their symbols. It was a nightmare. So I was looking at the maps at the map competition just this last month at the Institute, and they had an Alta NSPS map that was done on NAD 27.
Well,
So
I have a early checkbook cover with a set of 4-place trig tables in it that we used forever and ever for all our slope corrections. And I mean, a lot of them, I didn't even have to look in the tables. I knew them because we'd try and do an even degree or something like that to work out. And after you used it so many times, you just remembered what the correction was.
Yeah.
But yeah, it's nice now that I don't have to do this anymore.
You ever use one of these?
it's all by choice. I do what I want to do when I want to do it.
That's right.
Those of you that may have been gone backwards, let's take in the background. This is a stadia protractor.
Right.
There's a circular slide rule for reducing stadia readings.
Well, there's a lot of people that don't know the slope correction for correcting stadia distances on a slope.
Yeah.
And we used it all the time.
Got it reversed.
It's awesome.
Not that it made something questionably accurate more accurate, but that was the issue I had with it. I mean, what are we doing here?
Yeah. Before we bunch more jump off, I threw in the chat the YSN mentoring program is open for enrollment, and so we'll talk about it a few times this week. But there's if you go to the NSPS Young Surveyors Network, you can sign up to be a mentor or be a mentee. So those are open right now. If you guys want to click on those links there, or just go to the different websites, social media websites too. But all
Let
that's
me
open, so.
throw on a short advertisement here for round
Of course.
Tuesdays. We're starting it up again. We want to provide it as a resource for people to bring challenging projects they may want to have some help or feedback on. Right now, we've got a couple of us that are kind of working on organizing this, doing the initial presentations and stuff. But we want to get more people involved to come in and bring their stuff in where they can get feedback from other surveyors and stuff. So if you've got something that's got you a bit stymied, a little confused, or you want some additional feedback, and bring it on in. We're not there to criticize, we're there to help. Particularly if you're with a smaller firm, you don't have mentoring opportunities, or they're limited. This is an opportunity to listen to some of us old farts go on about some stuff and maybe give you a hand with some things.
Yeah.
Or if you know somebody that could take advantage of that, please pass the word around.
Yeah, Brad just threw in there about Kyle's last session. I did email him earlier this week, and I said, "Are you going to be ready to present later this month?" So, James, roundtable, we're bouncing around a little bit, but the next one will be tomorrow. And actually, Jerry's presenting tomorrow. He's got one that's working on some fractional section breakdowns. So, and then those are recorded as well, so you can go back and watch the last couple on those, James, on the roundtabletuesday.xyz website.
Hey, Jerry, are you coming to our Nevada, California conference?
It was a question I was just about to ask him. We're looking for a backup presenter, Mr. Jerry, because CFEDs may or may not happen. They have a budget meeting on Thursday. I'm sorry, on Friday. And so we might have to have a backup presenter on.
When is this?
That would be Saturday, March 29th.
Oh, I mean, it's like right away, huh?
Yeah. We won't know.
As
a last
I
second.
really should check with my wife first, but I'm
I
sure
know.
she won't mind if I
I know.
commit to something that could screw up her plans.
Right. So we'll see.
I just sent her on a cruise, so.
There you go. Yes.
Hope to see you, Jerry. I mean, you're definitely a huge asset to our profession.
100%.
Keep up the good work.
It's good stuff. I love it. Anybody got questions? Want to chime in on anything else? We do have all three this week. So mentoring Mondays, roundtable Tuesdays, and wisdom Wednesdays. So
busy week. So
it's a busy week this week. Yeah. Next week is NSPS spring meetings, NSPS student competition. So hopefully some of you guys will be around there as well. But lobby day as well on Tuesday next week. So again, another busy week, and then National Surveyors Week as well next week. So watch tons of social media for that.
You'll be up for the conference in
Yes.
Reno, won't you?
Yep, I'll be there.
I'm buying the beer.
All right, I come in Friday, so Friday to Tuesday.
Okay.
All right, everybody. That was awesome as always, Jerry. You do amazing.
Okay, thank you. Appreciate it.
Yep. Awesome, everybody. Have a great week. Well, I'm sure we'll see some of you tomorrow and some of you on Wednesday. Bye, everybody.
Bye.